Hello students, this is Dr. A. Sayyed. I welcome you all for the next class on matrix methods of structural analysis. We are dealing with unit number 5, that is Stiffness Matrix method for frame. In last class, we have solved one problem on analysis of portal frame using structure approach of Stiffness Matrix method. Today, we will solve the second problem on Stiffness Matrix method for portal frames. The statement of problem is analyze the portal frame as shown in figure using structure approach of stiffness matrix method. Take EI constant. So the given frame is having one column and one beam. Okay. Column is subjected to uniformly distributed load of 20 kN per meter and beam is subjected to central point load of 80 kN. EI is constant. We know that in the analysis of frame using stiffness matrix method, very first step is to determine degree of kinematic indeterminacy. So the frame is having fixed support at A. So kinematic unknowns are 0 at fixed support. There is no translation, no rotation at fixed support. Support C is having a roller support, and we know that support B, the joints where beams and columns are connected, those are called as semi-rigid joints, and these joints are subjected to rotations. So first unknown in the given portal frame is theta B, which is at point B, and second at support C, since a roller support is provided, roller support is subjected to rotation, that is theta C. Now because of this roller support at C, this frame becomes sway frame. Because of roller support, this frame becomes sway frame because this roller support allow point C to move horizontally towards right because of this uniformly distributed load over the column. So this frame is sway, and therefore the lateral sway will come in picture. So third kinematic unknown is delta, which is lateral displacement of point B. So third unknown is delta B. Okay. So dki of this frame is 3. See. So dki equal to 3. First unknown we have assumed theta B. Second unknown we have assumed theta C. And third unknown we have assumed delta, which is lateral displacement of point B. Okay. Now in the stiffness matrix method, we know that in the equation of equilibrium or compatibility condition, AD equal to ADL plus K into D. We have to determine all the matrices one by one. AD is equal to ADL plus K into D. So very first matrix involved in the compatibility condition is AD matrix. AD matrix stands for action corresponding to unknown displacement in the original structure. So AD matrix we will get from the original structures. So action corresponding to unknown displacement. Unknown displacements are, first is theta B. Corresponding action is moment at B. Second unknown is theta C. Corresponding action is moment at C. And third unknown is delta, which is lateral displacement of point B. Lateral means horizontal displacement of point B. If unknown is delta B, corresponding action is horizontal force at point B. Horizontal force at point B. These are the actions corresponding to unknown displacement. Moment at B, moment at C, and horizontal force at point B. So is there any moment acting at point B in the original structure? If you look at the original structure, there is no moment acting at point B. So this element is equal to 0. Similarly, if you look at the original structure, is there any moment acting at point C? No, there is no external moment acting at point C as well. So second element is also equal to 0. And last, third unknown is delta B. Corresponding action is horizontal force at point B. Is there any horizontal force at point B? No, there is no horizontal force at point B. So third element is also equal to 0. So all three elements are equal to 0 in AD matrix because there is no action given in the original structure corresponding to unknown displacements. Second matrix involved in the compatibility condition is ADL matrix. ADL matrix stands for action corresponding to unknown displacement in the restraint structure. Restraint means fixed structure. Action corresponding to unknown displacement. First unknown displacement is theta b. Corresponding action is moment at b. Second unknown displacement is theta c. Corresponding action is moment at c. And third unknown displacement is delta b. Corresponding action is reaction at b. Horizontal reaction at b. Okay. So in short, from the restraint structure we have to find out when you restrain the structure because of external load, what is the moment developed at point B? Moment at B. Then what is the moment developed at point C? And what is the reaction developed at point B? These reactions, actions we have to calculate from the restraint structure. For the simplicity, we will draw beam and column separately to understand the moments and reactions. Okay. So if you look at the first column AB, it is subjected to UDL. We know that in case of frame, already we have discussed in the previous problem, in case of frame, observer is always inside the frame. So we have to observe left column from this direction and beam from this direction. So if this is the direction of observation, if you look at this column, A is a left joint, B is a right joint. Okay. So anti-clockwise fixed moment is at A and clockwise fixed moment is at point B. Okay. Load acting over the column is UDL. So fixed moments are calculated using WL square by 12. Fixed moments are WL square by 12. W equal to 20, L is equal to 4. So if you substitute W and L in WL square by 12, you will get the fixed moment 26.67, which is same at both ends. Anti-clockwise at A means plus, clockwise at B means minus. Okay. Similarly in beam, it is subjected to central point load. So fixed moments are WL by 8. W is equal to 80. L is equal to again 4 divided by 8. Since we are observing beam from this direction, left end is B, right end is C. So anti-clockwise moment at B and clockwise moment at C. Magnitude of moment is 40. It is plus at B and minus at C. Once you calculate fixed moments, now we have to calculate the reactions. Already in previous problem we had discussed the delta, that is horizontal displacement. It is a displacement of point B in x direction, horizontal direction. So action corresponding to delta B is a horizontal reaction. Horizontal reaction occurs only in column because columns are subjected to horizontal forces. So no need to calculate reactions of beam. Only find out reactions of column. So how to find out reactions of column? Reactions are in two parts. First, reaction due to external load, that is UDL, and then reaction because of fixed end moments. So what is the reaction due to external load? UDL, intensity is 20, span is 4. So total load will be 20 into 4, 80, acting at center. So reactions will be half of this 80, that is 40 and 40. Since this UDL is acting towards right, reactions will be towards left. Okay, so 40 and 40, that is W by 2 or WL by 2, you can say. W 20 into 4 divided by 2 are the reactions because of external load. Now reactions because of moments. So reaction because of moments are equal to sum of moment divided by span. What is sum of moment? Plus 26.67 at A and minus 26.67 at B. Sum of moment. Plus 26.67 at A and minus 26.67 at B divided by span is 4. So sum of moment plus and minus, it is coming 0. This represents that there is no reaction because of moments. So there is only reaction because of external load, which is 40 at B as well as at A towards left because load is towards right. Okay, no need to find out reactions of beam. Now we have to write down ADL matrix. We know that again there will be three elements in ADL matrix, that is action corresponding to unknown displacement in the restraint structure. First kinematic unknown is theta b, corresponding action is moment at B. What is the moment at B? it is minus 26.67 in column and plus 40 in beam. Addition of these two, answer will be 13.33. Okay. Second unknown is theta c. Corresponding action is moment at c. What is the moment at c? It is clockwise 40, means minus 40. Okay. Third unknown is delta, which is delta b. Corresponding action is horizontal reaction at b. What is the horizontal reaction at b? It is towards left 40, means minus 40. Okay. So these are the elements of ADL matrix: 13.33, minus 40 and minus 40. Next matrix involved in the compatibility condition is steepness matrix. So now we have to derive the steepness matrix. We know that steepness matrix is derived by giving unit displacements one by one. There are three kinematic unknown displacement in this frame. First is theta b, then theta c and delta. So one by one we have to give the unit displacements. Okay. So first figure, let theta b equal to 1. Give the unit positive rotation at point B. Positive means anti-clockwise. Positive means anti-clockwise rotation. So rotate joint B in anti-clockwise sense by unit rotation. To rotate joint B in anti-clockwise sense, we have to apply moment in anti-clockwise sense. So this is anti-clockwise moment applied at point B. Okay. So if this is anti-clockwise, at far end also it is anti-clockwise. So nature of all moment will be anti-clockwise now. Magnitude of moment, we know that joint which we are rotating joint B. So at joint which we are rotating, moment is 4 EI by L. Right? It is 4 EI by L. Now in this problem, EI is constant given to you, as well as I is also same for both the members. Okay. So L is equal to 4 meter. So if you consider beam, it is 4 into E into I divided by 4. 4 cancel, magnitude of moment will be EI. Half of that 2 EI by L at other end. So half of EI is 0.5 EI. So these are the moments in beam. Similarly, 4 EI by L in column. L is equal to again 4 in column also. So 4 into E into I divided by 4. It is again 1 EI at point B. Half of that, that is 2 EI by L at A, that is 0.5 EI. Okay. So these are the moments required to rotate joint B in anti-clockwise sense by unit rotation. Now we have to find out reactions. We are interested in reactions of only column because action corresponding to delta B is horizontal reaction at point B. So no need to find out reactions of beam again. So how to find out reactions of column? There is no external load now in this. There are only moments at two ends. So reactions will be because of only moments. Reaction is equal to sum of moment divided by span. What are the moments? 1 EI at B, 0.5 EI at A. So what is sum of moment? 1 plus 0.5 EI. That is 1.5 EI divided by span is 4. Divided by span is 4. Reaction because of moments are equal to sum of moment divided by span. 1 EI plus 0.5 EI divided by span is 4. This answer is 0.375 EI. Okay. Since both the moments are anti-clockwise, the summation will be positive. Summation will be positive 0.375 EI. Positive answer represent it is anti-clockwise in nature. So reaction couple will be clockwise in nature. Clockwise means top reaction must be towards right and bottom reaction must be towards left. This represent clockwise couple. Okay. So top reaction, if you look at here at point B, it is 0.375 EI towards right and 0.375 EI towards left at A. This represent the clockwise couple. Okay. So this is first unit displacement figure. The second kinematic unknown is theta c. Okay. So now we have to rotate joint C by unit rotation. Now if you look at the given frame, when you rotate a joint C, since C is an end joint, when we rotate joint C, there will be no effect of this rotation on column. There is no effect of rotation of C on the column. So all the moments and reactions of column will be 0. All the moments and reactions of column will be 0, and that's why column is not shown in the second figure. Only the beam member is shown, because when you rotate joint C, there is no effect of this rotation on column. Okay, so if you look at the beam now, since we are rotated joint C, 4 EI by L moment will be at C and 2 EI by L moment will be at B. Okay, so if you substitute value of EI, which is constant, L is equal to 4. So if you substitute this L equal to 4, 4 upon 4, it is again 1 EI at C, half of that at other end, that is 2 EI by L, means 0.5 EI at B. No need to calculate the reaction because we are not. Now third unknown is delta, that is lateral displacement at point B. So third figure is delta is equal to 1. Give the unit positive horizontal displacement at point B. Okay, so horizontal displacement at point B. We know that the moment required to give the displacement in perpendicular direction is 6 EI by L square. 6 EI by L square. So if you substitute the values of L and EI, okay, L is equal to 4 meter for column. So 6, EI is constant, I is equal to I only. So if you substitute 6 divided by 4 square, that is 6 by 16. The magnitude of moment is 0.375 EI. 0.375 EI at both ends. Okay. Now we have to decide the nature of moment. So to decide the nature of moment, it's very simple. Draw one arrow in the direction of displacement. Since displacement is towards right, draw one arrow towards right and bend that arrow outside the column. That is anti-clockwise moment. Okay. So this is anti-clockwise moment. Magnitude is 0.375 EI. Now reactions because of moment. Reaction because of moments are equal to sum of moment divided by span. What is sum of moment? Both the moments are anti-clockwise. So plus 0.375 plus 0.375, that is sum of moment at A and B divided by span. Span is equal to 4. So if you use sum of moment divided by span, the answer is 0.1875 EI. 0.1875 EI. These are the values of reactions. Okay. Now, direction of reaction. If this answer is positive, since these two moments are anti-clockwise, that is positive, sum of moment will be positive. So this answer is positive. If answer is positive, the reaction couple will be clockwise. Reaction couple will be clockwise. Clockwise means top reaction must be towards right and bottom reaction must be towards left. So this produces the clockwise moment. Okay. So reaction because of moment in this column are 0.1875 EI at two ends. Top reaction is towards right and bottom reaction is towards left. Okay. So this is third figure, delta equal to 1. Now based on these three figures of unit displacement, we have to write down the steepness matrix. Okay. So from first figure, if you look at the first figure, so from this figure, you will get the first column of steepness matrix. What is the first column of steepness matrix? First unknown is theta B. Corresponding action is a moment at B. What is a moment at B? Here it is 1 EI and again 1 EI. Addition of these two, moment at B is 2 EI. Second unknown is theta C. Corresponding action is moment at C. So second element is moment at C. It is 0.5 EI. Okay. And third unknown is moment at, third unknown is delta, that is lateral displacement at point B. Corresponding action is horizontal reaction at point B and it is equal to 0.375 EI. Towards right it is positive. So moment at B, addition, then moment at C and reaction at B are the elements of first column of steepness matrix. Similarly in the second figure, that is theta C equal to 1. Moment at B is 0.5 EI. moment at B is 0.5 EI, moment at C is 1 EI, and reaction at column will be 0 because there is no column. Okay, so that reaction of B, horizontal reaction of column B will be 0. And now from third figure, the moment at B is 0.375 EI. It is anti-clockwise positive. Moment at C will be 0 because it is a delta equal to 1 figure, and delta, that is lateral sway, occurs only in column. There is no effect of this sway on the beam. That's why moments and reactions of beam will be 0. Okay, and that's why moment at C is equal to 0. So moment at B 0.375 EI, moment at C is 0, and reaction at B is towards right 0.1875. So all these three actions from each figure, if you write down in matrix form, it will give you stiffness matrix. So this is final stiffness matrix. Okay, first column from theta B equal to 1, second column from theta C equal to 1, third column from delta equal to 1. Understand again, this first element is moment at B in first figure, second element is moment at C, and third element is reaction at point B, which is horizontal reaction at point B. So same moment at B in the second figure, moment at C in second figure, reaction at B in second figure is the second column, and third column is in third figure, delta equal to 1, moment at B, moment at C, and reaction at B. Okay, this is K matrix. Now all the matrices are over. Finally we have to use the compatibility condition or equation of equilibrium, that is AD equal to ADL plus K into D. Okay, using this, substitute the value of matrix AD, then ADL, then K matrix just we have derived, and delta, that is vector of unknowns. You will get 3 equations, 3 unknowns. If you solve 3 equations, 3 unknowns in your calculator, this is final answer of kinematic unknowns theta B, theta C, and delta. Okay, once you find out these kinematic unknowns, now last step is to find out the moments, because if the statement of problem is analyze the frame, you have to plot the bending moment diagram. So we have to find out the moments finally. So we know that moments are calculated using the equation AM equal to, already we have used this equation many times for beam, AM equal to AML plus AMD into D. Okay, AM equal to AML plus AMD into D, where AM stands for vector of unknown moments. So unknown moments in the given frame are MAB, MBA, MBC, and MCB. Okay, so these are the unknown moments. Now values of these unknown moments in the restraint structure. Restraint means fixed structure. Values of these unknown moments in the restraint structure is AML vector. So this is MAB in a restraint structure, this is MBA clockwise, so minus, this is MBC 40, MCB clockwise 40 means minus 40. AMD matrix, this AMD matrix you will get from the unit displacement figures. First column from theta B equal to 1, second column from theta C equal to 1, and third column from delta equal to 1 figure. Okay, these are the values of MAB, BA, MBC, MCB in all 3 figures. And D stands for vector of unknowns, which we have determined now. So these are the values of theta B, theta C, and delta 1 upon EI outside. In AMD matrix also all moments will be in terms of EI, so EI is taken outside. So this EI and this EI will get cancelled. Now if you solve this AMD into D multiplication plus this AML elements one by one, you will get the 4 moments: 135.55, 25.33, minus 25.33, and 0. This you must get last element 0, because if end support of the frame is a roller or simple support, the moment at end support must be equal to 0. So moment at C, that is CB, must be equal to 0. Then only you can assume that your solution is correct. If it is not equal to 0, it means you made a mistake somewhere. Okay, so this is moment calculation. Once you calculate the moment, finally you can plot the bending moment diagram. Okay, bending moment diagram, since column is subjected to UDL, the simple moment, that is positive moments, will be parabolic in nature, and since beam is subjected to central point load, it is triangular in nature. These are the simple moments. And now moments, these negative moments, 135.55, answer is positive, means anti-clockwise. This answer is anti-clockwise. This minus represent it is clockwise. Okay. So MAB is 135 anti-clockwise. MAB is 135 anti-clockwise, means you must plot is towards left. This is 135. Then anti-clockwise B to A 25. So this is B. This is A. So B to A anti-clockwise means you must plot is towards right. So this is the deflected shape of or plot of negative moment. Then B to C, it is clockwise 25. Clockwise means it must be downward, you have to plot it, and then it is 0 at C. Okay, so this is the bending moment diagram for the frame. Okay, final bending moment diagram. Okay, so this is second problem for the analysis of frame using stiffness matrix method. In the next class, we will solve the third problem on stiffness matrix method for portal frames. Okay, thank you.